Swayam Prabha. Digital India. Educated India.
Good morning, everybody. In the earlier class, we were discussing varieties of vacuum gauges on thermal based gauges, ionization gauge based, ionization concept based gauges. We have also seen molecular drag based sort of primary gauges. We have seen McLeod gauge. We have seen U-tube manometers. We have seen capacitance as an indirect property, but rugged as a secondary standard. We have seen Bourdon gauges, which are standard mechanical gauges of high pressure, are extended towards this side. So, all these gauges we have seen for different purposes. They have got sensitivities and ruggedness and ranges applicable at various levels of vacuum. But now our game is towards high vacuum, ultra high vacuum. So, there we have seen Baird-Alpert gauge in the last class, how ionization is used. But that time we found the gauge is a hot cathode ionization gauge, otherwise it is very good case. So, you need to have a filament to produce electrons. Once the first electrons are produced, they are accelerated by a grid and they are made to get confused because of porous structure, and in the process long path is used to ionize them. That ions are proportional to number of atoms per unit volume, that is proportional to pressure. Fine. Over a period of time, people are facing some troubles. This filament gets cut, somebody does some wrong operation. So, people who are looking for some other way of using ionization only, but cold cathode, it is not hot cathode gas. Filament which produces electrons in hot cathode case, I call it cathode actually in hot cathode, but it is not hot cathode, hot filament. But instead of 3 elements like triode structure, if you have only 2 elements, then we will get cold cathode. But how do you produce electrons in cold? There are only 2 surfaces and you require electrons to be produced first, you require acceleration to that. So, high voltages are required and you require longer paths, that means some way of confusing the electrons is required, and you need ionization of the ambient atoms which are already in a rarefied atmosphere of -5 star, -6 star, and those ions have to be selectively coupled towards a cathode, and the original electrons should go into another electrode, but in the process they should ionize them. So, all these concepts together and ruggedness in a laboratory environment. So, lot of research was going on over a period of 15-20 years. So, one scientist called Penning came. So, he was trying to do lot of research on this vacuum measurement using a cold cathode gauge, and later he found some problems and reliability issues, but it is very friendly. Even today in our country, every laboratory has got Pirani gauge, Penning gauge, PP. So, most of the research laboratories in IITs, NITs, universities, even in industries etc., most of the vacuum companies manufacture only Pirani Penning gauge. Very few people manufacture ionization gauge or capacitance gauges, and they are so popular because they are rugged. And with proper precautions if you make, there are some foreign companies like Pfeiffer etc., they were labeled, they also Edwards, they also make very good Penning gauges with better quality also, reliability. So, let us try to understand what is this Penning gauge, what this scientist Penning did, in what way without any hot filament, how did he get ionization? Somebody has to ionize ambient. So, story starts with electron production. then electron acceleration, then accelerated electron confusion, long path, and that will be used to ionize. That ion current is a pressure equivalent signal. That is the story. So, what is it we are trying to do in penning gauge? How to confuse them? In hot cathode, how did we confuse? We put a perforated grid. It also used as a accelerating electrode for the initial electrons produced out of thermionic emission, but here the story is different. So, we will see how exactly it goes. So, the concepts that are going to be covered in this lecture are penning gauge, inverted magnetron gauge, which is a little improved version of penning model only. Without discovery of penning, these people could not have done that. So, once something is discovered, people start acting little bit small modifications and make it. This happens everywhere. Computers started, then additional this, additional that, they made better computers, better mobile phones, better display system. But starting point is difficult. PN junction making, PNP junction making, that is the starting funda. Semiconductors, it is basically solid state electronics. But now we will think digital electron is computer, we will forget that basic mechanism is semiconductors. Similarly, here basic mechanism is cold cathode ionization gauge, that is called penning gauge. These concepts we will see towards the end, since it is going to be the last lecture in the vacuum measurement. If time permits, of course, I will try to use some time to use some general methods of calibration of all the gauges that we have covered so far. So, let us be little brief, because we need to get time for everything. Okay. So, what is penning gauge? He discovered in 1937. I told you in the beginning history, production, measurement go hand in hand. If you produce something, you have to measure it. Again, better product you make, better measurement, then system design, then application, otherwise this product has no meaning. And if you cannot troubleshoot it, this will automatically die after some time. Okay. So, production, measurement, system design, application and troubleshooting, and of course, better display and better comfort and inexpensive, all this is a part of technology. Okay. Vacuum technology, which is a fundamental to several technologies, we have to understand gauges properly. So, in penning gauge, it is a cold cathode. Cold cathode means no heating effects are there. So, how do you produce cold cathode electrons? Now, forget about vacuum, measurement, etc. There are two surfaces, anode and cathode. Cathode is at negative potential, anode is at high potential. When you apply very high voltage, and if you can bring them nearer to each other, the field is very high, okay. Voltage will be there, but when you reduce the gap, field will be very high, and at some field, topmost electrons from this cathode, which are bound to the topmost atom surface layers of this cathode, they will be pulled out, tearing those electrons out of the top. This is popularly known as field emission. There is a spectroscopy associated with that, field emission spectroscopy, which will give you chemical analysis, because the amount of difficulty with which we pull, that is a characteristic of the chemical nature of that and all. I am not, we will see when analytical instruments are covered later in an application of vacuum later, XPS and ADAX and SCM, TM, they all require vacuum. We will see at that time these concepts. But for the present, you simply say the electrons can be obtained into free space between two electrodes, one cathode and one anode, by field emission. Once the electrons come out, they can be immediately going to the anode, but we should not do that. We want to confuse them. There in hot cathode we confuse it because of perforated. Here what to do? Magnetic field you apply. So, here now we come to the figure. We have two electrodes, two plates which are cathodes, which are connected commonly, and that is applied to a ground. It becomes negative if the other electrode is very positive. Ground is a negative with respect to a positive electrode. Why ground? Because these are all connected to the body and all shock and all. You cannot always have plus and minus. If you have high plus, even ground is negative. Okay. So, this anode is connected through a insulated bush here, which I have not shown here, but there will be insulated piece here. This collector terminal will be insulated from the body. If it is a glass, of course, anyway they are insulated, but otherwise you have to insulate this body, that is connected to the positive voltage, which is a high voltage of 3 kilovolts. So, and this is a ring type of electrode, and there is a axial there is a magnetic field perpendicular to these cathodes. So, now where are electric fields? Electric fields are like a basket, that is a top say basket, bottom say basket, because the anode is a ring, plates are there in between ring. These two cathodes are basically one electrode, they are connected electrically, the anode is this. So, this potential, this is one electric field will try to produce the field limited electrons, they will try to come and go to anode, but because of this magnetic field they will not cross the flux lines, they will be delayed, they will keep on rotating. I am not going into details of that electrodynamics, how the rotation motion comes, etc., and all forces due to magnetic field and a moving charge, these are all school stuff. Okay. These emitted electrons, because of high voltages, they are confused because of magnetic field, and they will take a lot of time to go to the anode. In the process, they will come across lots of atoms, they will ionize them. So, that ions density will be proportional to number of atoms per unit volume, and that is proportional to pressure. So, you can use this ionization of a magnetic field confused electrons coming from field emission without any hot filament, all that they have coupled, and Penning has made a discovery, and that is very popular today after almost 80 years. Even today it is a very important gauge. Most of the Indian industries manufacture this Pirani gauge and Penning gauge to measure low pressure and high vacuum, low vacuum and high vacuum. Okay. So, after understanding Penning gauge, but this Penning gauge, the way it is emitted first electron, the way it is confused, the way it is interacting, there are some errors, and also ionization depends on the nature of gas for the same amount of electron cross section to the atoms, etc. I will not go into details, but for a layman I will say, depending on the gas, the current for the same average pressure is independent of gas species, whether it is 100 molecules of nitrogen or 100 molecules of oxygen, according to kinetic theory, P is equal to NKT, that is all. It does not care about chemical nature of it, okay. Something like mole concepts, etc. Same here, here also the number density of atoms is proportional to number of electrons created, number of ions created, and that is proportional to the collision cross section of the few electrons which are available from field emitted. Thermionic emission in the ionization gauge produces lots of electrons. So, it is relatively easy to use these electrons and accelerate them, here very few. So, unless you use those few electrons with high voltages, accelerate them, but do not allow them to immediately get collected. They are created to do a purpose of ionizing them. If it goes immediately to anode, there is no use. So, you have to use high magnetic fields. There is no magnetic field in hot cathode, Bayard copper, Bayard Alpert gauges. Here we are having magnetic field. That is what we have seen. A cross fields of magnetic field and electric fields producing field emitted electrons and confusing them because of magnetic fields and using them to ionize and relating those ions to number density of atoms, and that is related to pressure. That is the principle. Same principle is extended in an inverted magnetron after 25-30 years by some other scientists called Hobson and Redhead. So, what they did was, because there were some errors coming, the electrons are interfering from the ion currents. So, what they did, there was a central anode which is like a rod, and there is a small cathode which is like a cup, but in between they introduced one more electrode which is at the same potential as the cathode, both are at the ground potential. Okay. So, this positive will be connected to the anode. So, that way this is called inverted magnetron. So, a strong magnetic field is applied here also. Its purpose is for confusing the electrons, so that they do their business of ionization before they get collected by the electrode. If they are collected by the cathode, these field emitted electrons, that will act like an error. We are not interested in measuring those electrons, we are interested in measuring ions, because ion current is proportional to pressure. So, these initially produced electrons, they should do their duty of ionization, but they should not be collected for the same collector cathode, or they should be collected somewhere. Okay. So, these electrons, if they, because if there is a outer circuit with this anode and cathode etc., and in between these electrons are interfering, that is dangerous. So, some other fellow should collect these electrons and ground them. So, that is why they have created one ground electrode. Voltage is between anode and cathode. If this was not there, these electrons also will be coming in a current, as a current in the opposite directions in with respect to external loop. But now, these electrons which are not proportional to pressure, they are collected by a ground electrode and goes to the ground, like phase, neutral and ground. Phase can also create potential difference with ground, as well as phase can produce potential difference with neutral, okay, in electrical industry. So, local thing is ground. So, that way by employing additional grade, what they did was, while cathode C is busy in collecting the anodes, this grounded additional cathode type structure, which is also cylindrical, that collects the field emitted electrons. That way the background error is less. Again, high voltage is required initially to produce high field to pull the electrons from field emission. That is always required, like a penning gauge, because there is no hot filament to produce thermionic emissions. So, when you come to the cross section of this, at this section, if you take cross section, this is my cathode, this C only I am plotting. Okay, I am not plotting this G. This is created by us to take care of this background field emitted electrons to be collected in between, not to interfere with the ion current, that is all. So, story is same again, the starting electrons coming from this high voltage, because of high voltage field emitted electrons from the anode, they come inside, they try to produce ions from the atoms, and these ions, where will they go? Because they are heavier in nature. These electrons, because of magnetic field, they are very light, they will be precessing around that. So, they will make all sorts of loops. Okay. So, these loops, what is the role of this loop making? To increase the path length, so that more and more atoms will come for a particular structure. There can be another structure, you can do varieties of gauges, and another calibration constant will be there for the ionization cross section with the atoms by these field emitted electrons. Initial electrons are very few. So, one electron, once it ionizes, 2 electrons are there, but this electron came out of the atom, but it has lost its identity. That is also, it looks like a field emitted electron. So, both of them will be accelerated by the electric fields, both of them will be confused by the magnet. So, it will be runaway process, after some time equilibrium comes. So, this cross connection of these things with an extra electrode, that has created a very good measurement down to 10⁻⁸ torr in inverted magnetron gauge. Beyond that, I can keep on explaining these things, but I think if you go to the internet, you will get very good, very long explanation with lots of derivations and all. Since lack of time, I will not be able to explain that, but this gauge is quite popular, and several versions of this gauge are being developed by several companies. Okay. So, these ions physically are collected by this collector, and the mass difference between ion and electron is exploited also. So, that rugged ions will not be going like electrons and making loop, they will be coolly collected by the collector. All these principles are used. This ion current is proportional to pressure with an index of k, this multiplier with k, and one power n is there. So, that varies from gas species to gases. All that calibrations can be done, and they can be used right up to 10⁻⁹ to -9 torr, and with cold cathode. So, maintenance is relatively easy. So, after understanding penning and inverted magnetron, after understanding hot cathode and Bayard Alpert gauge, all these gauges need to be calibrated again. Even the spinning rotor gauge needs some calibrations, and even McLeod gauge, and even U-tube, all these things, they require cross calibrations, and of course, thermal conductivity gauges definitely require cross calibration. So, when we come to the calibration of vacuum gauge, which is the final concept, I will spend some time, because we are coming to the end of the pressure measurement. Calibration is very important. What is it we are trying to measure? That is important. If you make one mistake, -5 will be measured as -3. then you will get a, instead of semiconductor, it will be some other insulator, oxidized. A silicon, for example, when you are processing under vacuum, it will be silicon. If you are processing under atmosphere, it will be silicon dioxide, which is a sand. It is no more semiconductor, which is an insulator. That is why semiconductors, there are two aspects. One is to make semiconductors, to make slices, that is the starting point. That entire manufacturing of semiconducting material requires vacuum processing. Once it is done, putting them in quick chambers and degassing them and making some treatment, etc., and sending it to the growth chamber, that is another story of growing various transistors, thousands of elements using VLSI circuit design, all that. But these are two aspects: semiconductors making, semiconductor electronics making, chip manufacturing, all of them require vacuum technology. Semiconductor manufacturing requires, because you will not make semiconducting oxides. Once it is done inside, monolayer formation should not be there, you should make P and N types and all those making things, and ultra high vacuum if you do not do, you will not get chip manufacturing. So, both of them require very good measurement of high vacuum. -3 torr, which has removed by 99.99, not good enough for semiconductor, nuclear and space technology and metallurgy. See, that is the beauty of vacuum technology. So, measurement has to be done with equal seriousness. So, every country has got a standardization things, calibrating the gauges that are manufactured by the companies, routinely used by the various types of customers or laboratory people or industries. They need to go out somewhere, they have to take these gauges somewhere, and what I am measuring, is it correct? That if they do not have confidence, a good semiconducting manufacturing company with proper calibration standards will be able to produce better chips compared to another semiconducting company. Semiconducting companies means two, either semiconductor making companies, silicon wafer manufacturers, metallurgical route, that is called semiconducting metallurgy, electronic materials, electronic metallurgy, or the other side, formation of thin film technology using PVD, CVD under vacuum conditions, and diffusion and growth, P type, N type, and heat treatment, gating and dielectric layers and plasma processing, all of that also requires vacuum. That is actual electronics making, electronic circuits manufacturing, which is the hardware aspect of computer chips, etc. So, this entire process should be done with proper gauges measuring, sitting in that chambers. So, whether it is proper or not, who will tell? Every country has got a standard laboratory. In India, we have at NPL New Delhi, we have that. Similarly, NIST is there USA, and PTB is there in Germany. They do this cross verifications of whether these primary gauges are really primary or not, using some still fundamental methods. What are those methods? Calibrations are done in these standard laboratories, whether it is NPL Delhi or PTB Germany, NIST USA, all the companies, whether it is customers of vacuum technology or manufacturers, they have to get it confirmed. Otherwise, quality control people will say that your outputs, whether it is a chip or whether it is a practical accelerator or whether it is any other nuclear device or a space technology, they will not be accepting, because you have to measure things accurately. So, there are two ways of calibrating the gauges. This can be developed in-house, but they are not easy. So, only very costly level, every country spends lot of money to make these level standards. One is to use the standards like your spinning rotor gauge or your McLeod gauge or YouTube, connect them with a T connection. This unknown gauge which is to be calibrated, this is a standard gauge using fundamental principles of Boyle's law, etc., and connect it to a chamber with a needle wall. You try to send some gas, and you, with a constant pumping speed or something, you try to measure. That is one way. Second way is by measuring the gauge at few fixed pressures, that fixed points are known fundamentally. That means, in that gauge, if you in that chamber which has been evacuated or you have done some magic in such a way, what magic I will tell you in the next slide. If you connect your gauge, you know that it is going to be 5 into -5. Whatever reading you are getting in your secondary gauge, call it as a 5 into -5. Then I will give another 5 into -6 and call it. You put this fixed point calibration and use it. So, how it is to be done is very interesting. We will see as time passes. So, calibration is done, somebody asks you how do you calibrate, up to 0.5 torr you can use U-tube manometer, which I have told you when I have covered in the primary standards, etc. And 0.5 to 10 power minus 5 McLeod gauge, this also I have told you, because you use Boyle's law at a constant temperature, calculate it back, Boyle's law coupled with U-tube creates a McLeod gauge. These two we have seen, and spinning rotor gauge also we have seen with proper calibration, but who will calibrate spinning rotor, that we will see later. So, all these calibration methods, capacitance gauge also I told you, it is a sort of calibration standard, but once it is calibrated, it will act like a secondary standard. So, these definitions vary from place to place. Okay. So, all of them are primary standards, you can call them suddenly, or secondary standards, but use standard word. But the normal gauges need to be calibrated. Whether you calibrate with a secondary standard or primary standard, it is up to you. Okay. Because your process should be reliable, so measurement should be reliable. So, spinning rotor gauge, capacitance gauge, McLeod gauge and U-tube manometer are the gauges with which, relative to that standard gauges, you are measuring your unknown gauges and calibrating, whether it is ionization gauge or pending gauge or thermal conductivity gauge or anything. That is one way of doing it. Other gauges, fixed known pressures, this is becoming very important, and these are maintained by the national facilities in every country. We will see how they are made. This is the last slide, but very important slide for you. There are two methods, one is called static expansion method, one is a dynamic method. These are fundamental methods, time and space invariant, whether you do this experiment in India or America, it is same. So, all that you need to do is, for example, static expansion method, the gauge to be calibrated is connected here, and there will be multiple volumes which are maintained at ultra high vacuum by a constant ultra high vacuum pump initially, close the valves, and their chambers should be such a high quality chambers, there should not be leak, there should not be degassing, and in between there will be walls, isolating walls, and in between there are small chambers which are also evacuated and sealed. So, all these things are various chambers, basically very high pure quality chambers. If you go to NBS, if you go to any PTB or NIST, you will see how beautiful that vacuum standard laboratory lab looks like. You cannot enter straight away, you have to enter through a clean lab, etc., because these are maintained with very cleanliness. Cleanliness is identical to, synonymous to vacuum, okay. Because of that cleanliness only, most of the applications of vacuum technology have come out, okay. So, this reference gauge, which is normally high pressure, 1 millibar, 100 millibar, or even 1 atmosphere, you can fill it with a known normal gauge like your Bourdon gauge through a small volume, and through this valve, but this measurement can be done very accurately, like 500 millibar can be measured very accurately. That is your P1, P initial in this volume. Volume can be measured by displacement technique, by water filling and taking down, but afterwards you should remove water vapor thoroughly, otherwise it will interfere with vacuum. That is exposed to a much bigger volume, capital V1, this is small V1. Then what will happen? P1 V1 is equal to P2 V2. V2 is this volume plus that volume. And while doing that, you keep this valve open and another small volume V2, that also let it be exposed. In fact, that V2 is the pre-volume to the next stage, but we are intentionally evacuating that by closing this valve and opening this valve. That means, all three volumes, small V1 and small V2 and big V1. In fact, in figure I am not showing it is a big, but it is a much bigger compared to these small volumes. All three are exposed. So, initial pressure is P1 V1, final pressure is P2, which we do not know, but it will be fixed as per P1, PV is equal to constant law. We need not measure it, it is going to be a fixed point. That will be P2 into small v1 plus small v2 plus capital V1. So, you have expanded static expansion. Static expansion, there is nothing dynamic, no piston, cylinder, nothing, no oil, no other concept, no electric field, no magnetic field, no fluid, nothing. Just you created one high pressure of a known volume and expand it to a bigger volume and another small volume through suitable valves, which have been initially evacuated by a high vacuum pump with another valve. Now, this as a whole, once you are done, now take that small volume again by isolating this. That is at some other pressure, but that pressure is a calculable pressure, because P1, V1, P2, V2, so you can calculate. That is exposed to the next stage, keeping the next of next stage ka prelude chamber. So, these 3 are now exposed to that now. Again another P3 will come, another expanded thing will come, and that will be exposed to the final thing. So, that way while multiple expansions you will get very good vacuum, but that vacuum is a calculable vacuum, not measurable vacuum. It is beyond measurement, and that if you connect your unknown gauge, that can be calibrated now using fixed point. And I will not go beyond that because it is a school stuff. See, for example, this P3 finally after 3 expansions will be, see, P1 into small v1 by this, and that will be another expansion, everywhere volumetric ratios will come. So, 3 volumetric ratios, initial volume, final volume, say, that will be multiple expansions with respect to initial high pressure, which can be measured very accurately. Then you will get a final unknown pressure, but calculable known pressure, which can be used to calibrate the gauge using simple Boyle's law. So, you can read all this and you can go up to 10 power minus 7 minus 8 or like that. This is one method of calibration. Okay. So, because of lack of time, I will not be able to explain beyond that. If you go through the internet, you will get lot of explanations on this, and every country has got a standard, and those countries standards are using either one of these two, mostly this. Second method is dynamic method. If you can measure accurately a mass flow rate of a leak through a very high quality leak wall, that mass flow rate in vacuum technology is called throughput, because pressure is proportional to density. So, if you can calculate throughput directly Q in vacuum technology standards, but indirectly mass flow rate only, and if that is connected to a high vacuum chamber, which is evacuated by a pump having a constant pumping speed over a pressure range, like diffusion pump, turbomolecular pump, all of them have got constant pressure range. So, that constant pressure range S is coupled to a very high quality vacuum chamber without leaks or degassing with an unknown gauge, which we want to calibrate now. We connect it here. This is Q and this is my pumping speed S. Throughput divided by pumping speed gives you one pressure, equilibrium pressure, that can be calculated by P is equal to Q by S. That comes out of calculation, we are not measuring. So, that P can be taken as the standard reference. At that time, whatever is the reading that we are getting in this ionization gauge or penning gauge or thermocouple gauge or whatever electronic reading we are getting, that reading is corresponding to this pressure, which is calculated by a throughput divided by a pumping speed. These pumps should be high vacuum pumps, chambers, walls, throughput calculations, everything if you do accurately, then final calculated pressure using this dynamic method, using a fundamental equation P is equal to Q by S of vacuum technology, you can use that as a standard thing for calibration of it. So, either use static expansion method or dynamic expansion method you can use and measure various high vacuum gauges, or McLeod gauge or YouTube manometer also you can use for standard references, and which one need to be again recalibrated. And high vacuum side you can use spinning rotor gauge as a standard gauge. You need not do this type of thing in your lab. You can purchase one spinning rotor and use it, or you can purchase capacitance and connect it -2 torque calibration. You can purchase YouTube manometer, or you can purchase static McLeod gauge. At the end of these things, all of them will go back to their respective national facilities, and all of those national facilities will be correlating further in international facilities, and this is how international standards are done, like length, mass, temperature, candela, all these standards are there, light, same thing here. Optical intensity is also there, all these standards have to be maintained, then only have meaning, then only is called physical measurement, otherwise it is only measurement, erroneous measurement, errors have to be minimized. The moment you are having secondary things, the calibrations have to be done, and that should be reliable calibrations. So, this way we have to take care of this. So, measurement we have covered various gauges, thermal conductivity gauges, ionization gauges, static expansion methods, calibration procedures, and care of the gauge, how to clean these things and all, that we will see in the system design. Depending on the impurities coming, the penning gauge need to be killed with ethyl alcohol or what, so that fresh surface will be there, otherwise ionization concept will be different. That I am not going to cover right now here. When we go for applications, whether it is a chemical industry or semiconductor industry, we need to take, it is called gauge care, gauge cleaning, that we will see later. Here in the measurement standard 5 lectures, we have seen various gauges at various ranges, various standards, various calibration procedures. With this, we have come to an end of measurement of vacuum at low, medium and high with relative standards at every range. So, with this we have completed measurement section, which is very important I think, and all of you have understood. So, whenever you are employed or you can have a self employment, you can create any of these gauges and say that my gauge is better than other gauge. If you can standardize, you have a very good startup. Thank you very much.